All right, howdy everybody. In this video, what we're going to do is talk about how to rank acidity of some NH containing functional groups. And as a reminder, there are a wide variety of videos on the Professor Carbon channel, and they're color coded so that you can find the questions that you're studying or learning about now. And so just as a reminder, the tag up top here tells you what kind of chapter it is, and the little explosion balloon up over here should tell you what kind of question it is, whether it be a mechanism or a synthesis or a bunch of reactions. In this video, we're going to talk about acidity, which I would call a general concept. And so the question here is to rank these from the most acidic to the least acidic, and it's specifically calling out the NH group. So let's just find those NH groups here. And so each compound has one of these NH containing functional groups. Now, acidity is one of these concepts that once you master it, it becomes quite easy, but often students struggle to get to that level of proficiency. And it's partially because a lot of different concepts can influence how acidic or basic a functional group is. In this case, we're talking specifically about acidity, and all of these molecules are neutral intermediates. And so in each case, we're talking about going from an NH in equilibrium, if it's a pKa, to H plus our amine minus. And so typically when we talk about the acidity and when our product is anionic, what we tend to do is talk about how stable the anion is. And really there's probably three kind of core attributes that might influence how basic or acidic a group is. And so I always like to think about them as what atom is the charge on. And the reason I say that is generally this is correlated with electronegativity. So carbanions end up being quite basic. So methyl anion, we usually invoke having a pK of about 50. N- groups, things like diisopropylamine or just ammonia, NH3, are also quite basic when they're anionic. And so we usually invoke a pK of about 38 for ammonia. Then we have O-, and most students are familiar with hydroxide, and that's kind of one of the most comfortable negative charges that they tend to have. And water's pKa going to hydroxide is about 15-ish. And so that works quite nicely. And so if you notice, we're following the periodic trend with electronegativity, and that helps roughly with X- as well. And here X- is things like chlorine, bromine, or iodine. And of course, HCl is a very common strong acid, and typically we invoke it having a pK of about -7. And so that follows roughly delta 20-ish pK units here and another delta 20-ish pK units here, give or take a couple. And so this follows with the electronegativity just going right across the periodic table. All right, in this case, all of these NH compounds contain a nitrogen group, and so we're going to invoke the N- in all cases. And so what that means is we can kind of scribble out some of this stuff that we're not going to talk about. So within the N- groups, then we want to default really to two separate kind of concepts, one of which is resonance, and the second of which is inductive effects. And when we talk about inductive effects, we're talking about proximal electron withdrawing groups that are not resonance delocalizing. And generally, resonance is going to be more powerful than inductive effects, generally speaking. And the classic kind of example that is used to illustrate that is if we look at something like trifluoroethanol, and we compare that to regular old ethanol, and we compare that to acetic acid. You know, the pKa of ethanol is pretty close to hydroxide, and so we usually say about 16 for that. Trifluoroethanol comes in at about 11, so quite a bit more acidic than ethanol. but not as acidic as acetic acid. And acetic acid comes in at about 4.75. And so overall, the resonance delocalization of this anion in the acetate functional group, I'm going to use my resonance arrow here, is really what we usually use to explain that increased acidity. And so for the nitrogen-containing molecules across the top, what I would encourage you to do is to draw the anions of each of these intermediates and then consider how many different places and in what kind of functional group that negative charge is delocalized. And so let's just start here with N-methyl benzamide. And then our next one was the phthalimide anion. We have an additional couple of groups here. And the last one was kind of an unusual sulfur-containing compound, but it turns out it's actually quite a common molecule. So saccharin is an artificial sweetener. Okay, and so these are the corresponding anions for all of the NH-containing starting materials that were drawn up above. And let's just consider now if there are any places we could delocalize this negative charge via resonance. And so in that starting material, we definitely can delocalize up into the oxygen. And so that would lead us to intermediate like this. And so I'm now gonna rank these based on how many resonance structures there are and what kind of heteroatom they are. And so I would say that this is one res and it's one oxy-res. So we put that negative charge on an oxygen. If we compare that to the phthalimide anion right next door, now we could delocalize this negative charge up. And so that would give us this resonance structure. And I think we can also take that charge and send it all the way down to the other oxygen as well. And so here now we have two res, and both of them are oxy resonances. And so in both resonance structures, we have a negative charge on oxygen. We then can compare that to saccharin, and it turns out saccharin is going to have the exact same kinds of resonance structures. And in this particular case, though, one of them is going to be on oxygen. And then if we take those electrons and swing it all the way down, we can put another one here on this other oxygen. And then we can move that negative charge to the other oxygen. And so in this case, now we have three resonance structures, and they're all going to be on oxygen. So we got one here on oxygen, two on oxygen, and three on oxygen. And so that really helps out. That's a pretty delocalized anion. All right, and the last one here now, we're going to have a variety of resonance structures. And so we could take this up and put it on oxygen, just like we've been doing for the rest of these. And we can also then delocalize this negative charge into the benzene ring. And then we can take that negative charge and move it around the benzene ring. And so now we have 4 different resonance structures. So 1, 2, 3, 4. And so it's 1 on oxygen and it's 3 then on carbon. And so much like our discussion up here where I said it's really dependent on what kind of atom you're putting this negative charge on, the same thing is true with our resonance structures. And so the good news though is we can at least rank these from the least acidic, and let's just make sure we reread our instructions here. The least acidic should be compound 4. And that should be the one that has only 1 resonance structure. So everything else has more than 1 resonance structure, and all of those other compounds have at least 1 resonance structure on oxygen. And so let's make the N-methyl benzamide our least acidic group. And so there you go. So that is by far and away the least acidic because it has the least stable anion, and the way that we justify that is because it has the fewest resonance structures. Now we have a tough choice for the next one because these two both have multiple resonance structures. This one only has 2. This one has a total of 4. And so now we have an issue because we can't just go with what is the most number of resonance structures. We have to consider what those resonance structures are. And because O minus is so much more stable than C minus in general because of the electronegativity of oxygen, this one, it turns out, is going to be more stable than this one. And it should be by a decent margin. So even though the acid aniline here has more resonance structures, because those are carbon-containing resonance structures, they're going to be less significant to the overall resonance hybrid. Because oxygen is a very powerful electron or electronegative atom, it's going to be willing to soak up and absorb all that electronegativity onto itself and all that electron density. And so that's going to make this one the next most stable. So we're going to rank this one 3, and this one's going to be 2. Here we go. And then saccharin is going to be the winner. It's going to be the most acidic. And the reason it's the most acidic is not only does it have 2 powerful electron withdrawing groups on them, one of those is a sulfonyl group. And it becomes very stabilized, much like sulfuric acid. And so when I see these kinds of sulfonamides, I think about kind of a nitrogen-containing version of sulfuric acid. And that SO2 group is a very powerful electron withdrawing. And hopefully that makes sense because it allows not only 1, but 2 resonance structures where we can distribute that negative charge on 2 different oxygen atoms. And so this molecule saccharin being able to distribute that negative charge across 3 different oxygens is incredibly stabilizing to the anion. And that means that the NH group will be quite acidic as a counter to that. All right, hopefully you found this video helpful. Please continue to watch those on the Professor Carbon channel. For those of you that are already not subscribers, please do subscribe to the YouTube channel. That lets us know that these videos are helping people, and it gives us encouragement to continue to make a couple of additional videos. For those of you that are really excited and you want access to the questions, both in the PDF form before and after I've kind of doodled on them, you can go ahead and access those in our Patreon page, which you can click above in the banner for the Professor Carbon YouTube channel. So please tell your friends about us, and please watch the next video.